Okay, so today we're going to talk about position, displacement, velocity, speed, all those good things. So we started talking last time about how we might have a position for an object, which I'll use either s or x for the position vector depending on how I'm feeling at a particular time. And our position vector might have an x, a y, and a z component. So for example, if we have a coordinate axis, this point right here, the position vector of this thing, which I'm going to call S0, so this is the place where it starts off. The initial position here might be, say, -2, +1, and 0. If we have if our object in question moves, right? So we start off at -2, 1, and we end up at another point.
Professor, we can't see your screen.
Oh, thank you very much. Is that better?
Yes, sir.
Okay, thank you very much. Right, and I can't see the chat at the same time I'm drawing, so so feel free to unmute yourself and speak up. Thank you very much for doing so. All right. We start at some position on our plane. We end up at some other position. What is the displacement that our object has experienced going from S0 to S1? Right, so the displacement is going to be a vector, and it's going to be where we ended up minus where we started off. So in this case, the displacement that we experienced was 4, -2, 0. So that's our displacement vector for this movement. A related question is, what distance did we cover in that time? So the distance is the magnitude of the displacement vector. So in this case, you'll recall from last time, we used the Pythagorean theorem to get the magnitude or the length of a vector. So in this case, we're going to have 4 squared plus 2 squared. 4 squared is 16, 2 squared is 4. So we're going to have, our distance is going to be square root of 20. If we know how much time it took to go from 0 to 1, then we have a way of talking about our average velocity in that time. So we might not be at the same velocity at every moment, but the velocity is in general, remember in our general case, we said that velocity was the derivative of the time derivative of displacement in this case, we have just enough information to talk about the average velocity. So our will be our displacement vector. Right? This is the distance that we traveled in a certain amount of time. So the book refers to this second form here as the average velocity and this first form as the instantaneous velocity. So this is the exact velocity at any given moment. Average velocity will just give us the velocity, averaged over a period of time. We make one more distinction at this point. We want to be able to talk about the speed of an object. So just like distance is the magnitude of displacement, speed is the magnitude of our velocity. And we will find the magnitude of that the same way that we did for distance. We're going to use the Pythagorean theorem on our vector. There's a thought problem that I like to tell to kind of illustrate the difference between all of these things. Let's say that you get up in the morning and you jog to a coffee shop, which is a kilometer down the road. You grab yourself a coffee. It takes you 6 minutes to jog to the coffee shop. It takes you 6 minutes to order a coffee. It takes you 6 minutes to jog back home after getting your coffee, which you then drink before you take a shower. What is the total distance you traveled during this coffee outing? Feel free to type your answer in the chat. Or failing that, I will just call on somebody. Kelvin, excellent. You have traveled a distance of 2 kilometers. 1 kilometer there, 1 kilometer back. Related question. What is the displacement that you have experienced during your morning excursion? Let's go with Blanco. What do you think, Matthew Blanco? All right, Mr. Blanco is not available. Broken recorders. What is the displacement that you've experienced over your kilometer jog to the coffee shop, kilometer back? That's right. Yeah, your total displacement is 0. You started at home, you ended at home. And our displacement is where you ended up minus where you started. In this case, you ended up in exactly the same place that you started. What is the speed, your average speed during your trip to the coffee shop and back? Derby Calderon? What's your speed during this outing? Nothing from Derby? Okay. Roberto Morales. What's your speed? No? Okay, so we've got some people in the chat who are not... Oh, would it be 1? Um, can you tell us your reasoning there? You can feel free to unmute yourself if that's an option for you. Yeah, Caleb Nolly says D over T, distance over time. Yep, so your distance is 2 kilometers, your time is 18 minutes. So whatever that comes out to, a kilometer per 9 minutes, that's going to be your speed. What about your velocity, your average velocity? Gunderson, you're next on the list. It's good. I don't know is always an acceptable answer. So our velocity, so our speed, we can think of as our distance over time, but our velocity is going to be our displacement over time. And broken recorders already let us know that our displacement was 0. So if our displacement is 0, then our velocity has to also be 0. That is, you jogged 1 kilometer in the direction of the coffee shop, and you also jogged a kilometer away from the coffee shop. So you spend an equal amount of time with a velocity toward the coffee shop and away from the coffee shop. It cancels out to 0. Do we have any questions on this first page so far?
For time, would it be 12, not 18?
Oh, 6 minutes there, 6 minutes ordering coffee, and 6 minutes back.
So we count the 6 minutes waiting for the coffee?
We do. So the whole time between beginning and end.
Okay, thank you.
Yep. All right. Let's move on to a second page then. All right. Last time we used integration to derive 2 equations based on an assumption of constant acceleration. So acceleration is the one that we haven't talked about yet today, but acceleration is going to be the rate of change of the velocity, just like velocity is the rate of change of the displacement. Now, there's no guarantee that acceleration is going to be a constant in general. But if acceleration is a constant, then we were able to use some integration and show that our velocity as a function of time is equal to whatever velocity we started out at plus an AT term for acceleration. We were also able to show that our position as a function of time is equal to whatever our starting position was, plus a term related to our initial velocity, plus a term related to our acceleration. There is a third somewhat useful formula that we're going to derive together. It's relatively simple, but it's frequently useful to have a relationship that does not involve time, right? So if we take our expression for velocity here and we solve for time, so we can say t is equal to v minus v naught over a. And here we are implicitly going to one dimension at a time. So notice that dividing a vector by a vector doesn't actually make any sense. But if we take just the components, right? So if these are just the x components, for example, now this expression makes sense. And if we're looking at just one dimension at a time, we can take this expression for time, plug it into our second formula for x as a function of time. So x equals, and I'm going to drop the subscripts here because it doesn't actually matter which direction we're looking at. As long as we're only looking at one component at a time, this is a valid derivation. All right, so we've plugged in our expression for time. We're going to do some distributing. We're going to move this x sub 0 to the left-hand side of the, well, we're going to move, yeah, for the moment, we're going to move the x sub 0 to the other side of the equation. We're going to square a binomial up here. And notice that when we have an a squared in the denominator here and an a on the numerator, that we're going to get some cancellation, and we're going to end up with just 1a in the denominator. And then our numerator here will be v squared minus 2v v naught plus v squared, v naught squared. All right, and we're almost done now. We're going to do some distribution and break up these terms by themselves. So here we've got v naught v over 2. Or sorry, not over 2, over a. My own handwriting is getting the best of me. I'm going to pair this with the middle term from this second half here, where we have a 2 in the numerator and a 2 in the denominator. So we're going to get a minus v naught over a. These two terms are going to cancel. And then we will have a plus v squared over 2a plus v naught squared over 2a. These terms cancel, multiply everything by 2a, and we're going to introduce one little bit of notation. It's frequently convenient that when we have a change in a quantity, like this, x minus x naught, that's the change in position, that we're going to go ahead and press a delta into service to indicate the change in that quantity. We've multiplied by 2a, and on the other side, v squared I've lost the negative sign. Yep. There we go. All right, so we have an expression involving distance, acceleration, initial velocity, final velocity, but which does not involve time at all. So these three are going to be our equations of kinematics if velocity is a constant. And these are going to be the first three tools in our toolbox. Now, of course, acceleration doesn't have to be constant, and we know enough calculus to be able to take any arbitrary expression for acceleration, integrate a couple of times, and find an expression for position. But at least in the first half of this class, we are going to often enough have constant accelerations that it will be useful to keep these three formulas close to heart. So, since we're here, let's talk about our toolbox. We're going to be populating it as we go along in the semester. There's not going to be very many things that we put in here. We're going to start with kinematics. Kinematics is the study of how things move. We're going to set aside for the moment the question of why things move. We'll get to that in chapter 5. But first, we're going to talk about how things move. And if acceleration is a constant, we have three formulas which we can use to solve a large variety of problems. These are the first three tools we're going to put in our toolbox. There won't be any new tools in the next chapter. So chapters 3 and 4 are going to be just these three. That's it. Any questions on this second page?
Will we have to prove this or rewrite all this in the future at all?
No. Not that it would be very difficult, right? Like it's only a few lines of derivation, but in general, I'm going to ask you to analyze situations and not do proofs.
All right, thank you.
Mm-hmm. Any other questions?
Is there a general like situation or like reason that I could write down for like when or situations when I'd be using each of these equations? Like a quick little bit I could write down somewhere.
In general, no, because there are thousands of possible situations that we could use these three equations on. We're going to do a couple of problems today, but in general, we're going to have to look at what it is we want out of a situation, out of an analysis, and what it is we already have, and then we're going to look at the tools in our toolbox. Say, well, which of these can give us the thing I want, and that's the one that we're going to pull out of the toolbox. Prada, yeah, acceleration is the derivative of velocity. Or just like we defined an average velocity on the first page, we could also talk about an average acceleration, being the total change in velocity over, some finite period of time. Hey, anything else before we move on? Okay. Oh, yeah.
Just one last thing. So I get so like V's velocity, T's time, V naught is starting velocity, A is acceleration. What's X and X naught represent again?
Position. So
Position. Okay.
yeah, X doesn't necessarily, there's, I'm going to make an effort to use S instead of X when I'm talking about a multidimensional position. But there's some I guess lazy habits that I've got, and that as engineers you will undoubtedly develop as well. But yeah, so X with a vector hat doesn't necessarily mean in the X direction. It just means a positional vector. Does anybody have any problems that they had trouble with over the weekend that they would like to have worked on now that we should do together? All right, well, let's do a couple of problems since we're here. I expect that probably everybody is going to be working. So I'm looking at the OpenStax textbook right now, and in Chapter 3, there's actually 4 different kinds of problems. There's conceptual questions, there's problems, there's additional problems, which are like slightly more difficult, and then there's challenge problems. So in class, I'm probably going to be working challenge problems mostly, because they can be relatively complicated. For your own practice, you should be doing, for sure, conceptual questions, problems, additional problems. Test problems and quiz problems will be at the difficulty of additional problems. So conceptual questions probably won't ask any of those on quizzes or exams, and then the ones that the OpenStax book labels just problems are a little too easy. I think they're like one-line solutions most of the time, but the difficulty level in additional problems, that's where I'll be able to see what you've got on quizzes and exams. So my philosophy is always, if you practice on things that are more difficult than the test will be easy. So that's what we're going to do in class. We're going to work challenge problems together. All right, any comments or questions on that? So we're going to start with question 112. So we have at least two people running a 100-meter race. The winner is timed at 11.2, which is fast, maybe not Olympic record fast, but it's fast. The second place finisher's time is 11.6 seconds. So the winner wins by 0.4 seconds. But the question is, by what distance did the winner win over the second place runner? So we're going to practice, even though this question is not necessarily super difficult, we're going to practice good habits. Last week I started talking about mise en place for our problems. It's French for everything in its place. So before we actually pull out anything from our physics toolbox, we are going to start putting everything in its place. And we have a method that we're going to try to practice. So whenever we're dealing with any new problem that's even a little bit difficult, we're going to draw a picture. Second, we are going to specify the coordinate axes for the problem. Third, if there are any vectors, we're going to break them down into their components. Only then are we going to reach into our toolbox and decide what physics might be appropriate to this problem. And then finally, we are going to do the math. All right, so let's draw a picture. A good picture is really essential to understanding what's going on in a physics problem. So we have a racetrack. It is 100 meters long. And we have two runners that we are interested in. We have green runner, and we have red runner. The finishing time for our green runner, 11.2 seconds. Finishing time for our red runner is 11.6 seconds. We are very interested in finding out what is this distance here, which I'm going to label R. What is this distance between the two runners when green runner is crossing the finish line? All right, so this is that's step one of our problem. Step two, decide on your coordinate axis. Here, there's not really anything fancy going on. In fact, we can just say that to the right is the positive x direction, and we're not even going to use the y direction. 3, there's no vectors since everything is one-dimensional in this problem, so we don't actually have to break out any vectors, which is nice. And then fourth, physics. So the problem says to assume that the velocity of each runner is constant throughout the race. So to me, that indicates that if we can, we would like to find out what that velocity is. So we don't have very many tools, but we've got something like distance, acceleration, time, initial velocity. So we're going to pull out our K2 from the last slide. Right? K2 is distance as a function of initial velocity, time, acceleration. So we'll pull that out. Notice I'm not putting any vector hats on anything this time because we just have a one-dimensional problem. Everything is just in the x direction. Do we have any questions so far? All right. What is the acceleration that these runners are undergoing? Let's see, who have I not called on? Kanoa? Oh, we have a question. Tieta, so how do we know which of the equations will go with the problem? It's an excellent question. Let's take a look at what we have in our toolbox so far. So we don't have that many tools, so if we guess at which tool we need and we guess wrong, the stakes are very low. So before we move on with this equation, which is actually going to help us, let's see what would happen if we tried to bring in one of the other two instead. So what if we tried to use the first one? So v squared minus v naught squared equals 2a delta x. Okay. Do we know? We don't know what initial velocity or final velocity is. So that's two unknowns. We also don't know what acceleration is. So that's three unknowns. Is that a solvable problem? Like, do we have a way of figuring out, initial velocity, final velocity, or acceleration? Like, what? In fact, I was trying to ask, like, what is the acceleration that these runners are experiencing? I was hoping that Kanoa would have an idea about that. You can either unmute yourself or type in the chat. All right. How about Kelly John? It's all right. If you say you don't know, that's fine. Kelly John, what do you think? What acceleration are these runners experiencing? Oh, yeah, you're right. Kanoa, you thought about it for a moment? That's correct. The acceleration is 0. The key idea here, right? The velocity of each runner is constant, right? The acceleration is the derivative of the velocity. If the velocity is constant, the derivative of that is going to be 0. So constant velocity means 0 acceleration. So if we have 0 acceleration, right? This number here is 0. And if the velocity is constant, that means initial velocity and final velocity are the same. So our third kinematic equation just gives us 0 equals 0. That's not super helpful. So if we go down that rabbit hole, that blind alley, it's a short alley at the very least. But we work on it for a minute, we realize that this isn't helping us. We're going to have to go back to the toolbox and choose something else. So what about if we, so this is K3. What if we tried to pull out K1? Right, what we get here is we just decided that acceleration is 0. So all this gives us is v equals v naught, which we already knew, so that's not super helpful. So since we tried K1 and K3, neither of those gave us anything, we can go on to K2. So acceleration is still 0, which means that this whole term here is going to be 0. But, also, this is supposed to be a t. At the beginning of the race, the initial position of the runners is 0. The final position is 100. The initial velocity we don't know, but the green runner is going to take 11.2 seconds. So actually, K2 gives us some information. We have only one unknown, and so we're able to solve for it. So v naught equals 100 over 11.2. Right, I plug that into my old reliable, and we get about 8.9 meters a second. So, Derby Calderon asks, where do you find the challenge problems? I will show you that in just a moment. Palencia, so let's say it was like real life. It's like if the runners were just instantly fast from the start since the velocity is constant. Yeah, that's right. So we're not for the moment, we're not allowing that. You do need a speed up time. We definitely could do that, but since we're just starting out, we're simplifying a few things. So instead of taking like 1 second to get up to speed, we're just going to say that your top speed out of the gate. All right. So similarly, we can find an initial velocity for the red runner. Red runner takes 11.6 seconds to complete the race. So they are a slightly slower 8.62 meters per second. 8.6. All right. Now we can actually aim for the thing that we're interested in. OTA to round off by 1 decimal. It felt right. There's some rules for significant figures in Chapter 1, but really as long as you include a reasonable number of decimals, I'm going to be fine with it. So we're interested in the distance between the runners. We note that the green runner is at 100 meters already. And the red runner is at whatever distance he's at, 11.2 seconds into the race. But since we know the red runner's initial velocity, we actually have a way we can figure out like at what point in the race is he after 11.2 seconds. Again, so we're going to go back to K2. We're going to use K2 to figure out this x of 11.2. At initial position is 0. The next term, v naught t, so minus 8.6 times 11.2. And then the last term, acceleration is 0, so that's 0. So our final answer is 100 minus 8.6 times 11.2, or about 3.68. It's like 3 or 4 strides at sprint speed. So not a very big gap at all. All right, any questions on this working here? Questions, comments?
So we can expect this question or something similar to be on quizzes, right, and tests?
Yeah, Probably something simpler than this, but similar to it, will be on the quiz for Wednesday.
And to get full credits or full marks, we would have to show the kinematics equation that we use.
Yes. To get full marks, you're going to need to show me each of these 5 steps. That you draw a picture, you have your coordinates, you broke down your vectors, you chose a piece of physics, and you did the math.
All right. Okay. Thank
So,
you.
Doing it, having you upload an image for your quizzes instead of like doing a multiple choice quiz means that I can give you partial credit too. Which means that if you, if you do the work, you do some of the intermediate work right, and then you do something like 2 + 3 = 7 on the last step, I can still give you most of the points.
Okay. This is a late question, but could you explain what not is?
Yeah, so this subscript 0. So if we have v sub 0 or x sub 0. The subscript 0 is usually read as not. So v naught. And what we mean by that, right? So v naught means the velocity at time t = 0. Does that answer your question, Kelvin?
So it just means initial, right?
Yeah, it just means initial.
Okay. Thank you.
All right. Broken Recorders asks, what's the formula for R that you used? So that is actually just an analysis of the picture here. So where's my red? There we go. So the distance that the red runner has covered was x of 11.2. The distance that the green runner covered was 100, and this little bit r is just the difference between them. Does that answer your question?
This might sound dumb, but so when we're talking about like meters distance, how are you multiplying it by time, right? And getting still a meters answer, you know what I mean?
Oh, you mean like right here?
Yeah, like you're doing 11.2, it's seconds, and then you're also trying to do time, which is meters. Wouldn't that give you an answer that's like meters per second at the end?
So I mean, that's a good question. What I'm writing here is not x times 11.2, but x of 11.2, in the sense that if we wrote like f of x equals 3x squared, right? So yeah, so the 11.2 is the argument of the thing. Does that make sense?
Okay, yeah, yeah. No, I was thinking it was like you were multiplying, and that didn't make sense when I was thinking about it. I don't know. Okay, yeah, that was it.
Cool. Right. Any other questions on this position x at time t? Yeah, that's what I'm meaning. So x of a number means position at time, whatever is in parentheses. Okay. So let's talk about where to find the problems to work on. So here's the OpenStax textbook. I actually pulled this problem directly out of the textbook. Click on Table of Contents. Under Chapter Review, there will be conceptual questions divided up by section. There will be like simple plug-and-chug problems, again divided up by section. And then additional problems. These are a little trickier, and they will incorporate more than one section at a time generally. So like this professional baseball player Nolan Ryan, This is going to be a combination of like 3-1, 3-3, 3-2, and 3-4. So additional problems, these will be like the level of questions that I'll ask for quizzes and tests. And then the ones we do in class will be the slightly more difficult ones, the challenge problems. So these challenge problems will require you to not just to synthesize the different sections together at once, but also to do something interesting mathematically, usually. All right. Did anyone sign up for Expert TA to get to do their problems? Or did anyone try to and was not able to? Derby, that's right. The textbook that we're using is University Physics. College Physics is the algebra-based course. That's what they would use for Physics 151.
Whoops. That explains why things were a little weird.
You all right there?
No, I was just saying. I forgot my mic turned on. No, I was using the college physics book. That's probably why things were a little weird when I was reading through them.
Yeah. So as engineers, you're going to want the more detailed analysis that you get from the university physics book.
Yeah, I didn't realize that there was the two different ones. Usually people say college and university. You know, they're like synonyms for each other.
Yep. Well, it's good we caught this early. So there are some interesting problems in the college physics book. There's a lot of like, they try to do like medical applications because most of the people using it are pre-med majors. But yeah, we're going to be using the university physics book. Palencia asks, should we sign up for Expert TA later on in like a week or two, or should we do it ASAP? I mean, the sooner the better. So I'm going to be putting together questions on a weekly basis for Expert TA from their problem pool. And so it's like the longer you wait, the more questions you'll have to get through before you get to the good stuff. Does the syllabus have the college physics link? Well, I will fix that today. I will upload a new syllabus this afternoon with a fixed link. Thank you for bringing that to my attention. All right. Any other questions, comments, issues today? If not, I mean, if you're welcome to go and enjoy the rest of your day. Same meet, same time on Wednesday. Hopefully next week we will actually have our WebEx up and running, or maybe we'll just love Google Meet so much we won't use it. But yeah, so same time on Wednesday. There will be a quiz first thing for real. I'll see you then.
I just want to confirm something real quick. So at this point, we should have already read half of Chapter 3 and all of Chapter 2.
Correct.
Okay. All right. Then I'm going to have to redo that because I had the wrong textbook.
Oh, at the beginning, it's mostly the same.
Okay. Okay.
Are we not supposed to read chapter 1, by the way? I just joined this class. It was me. But, so chapter 1 wasn't a part of it?
I mean, chapter 1 is like basic science stuff like significant figures and what do you mean by a hypothesis. So, yeah, we're not going to cover that, but if you want a refresher, you can go ahead.
Yeah, could you also tell me where Expert TA is? Is this on the website?
Yeah, so it should be in the syllabus. There's also a discussion discussion on it on Canvas, but it's a third-party physics homework site. It's pretty cheap. I think it's $35 for this semester, and a lot of problems to work on there. And I'm using it since I'm not collecting any homework. This is one of the options that I'm giving for problems. So if you do the expert TA problems, I see that you've done it, and then you get some extra credit on the final for it.
Okay, yeah, that would be great actually.
So
All right.
there should be some information on that in the syllabus, and then also check the discussions on Canvas.
All right.
So Caleb, did that answer your question about what expert TA is? Okay, awesome. See you next time, Kelvin.
This quiz that's coming up, is that only going to be on the first half of 3.2, or is it going to be all of 3.2? Or all of Chapter 3?
Yeah, up to 3.4.
Okay, up to 3.4. Okay.
Since that's what we covered today.